Hello everyone, this is Hazare and today I'm going to present this survey on dropout methods and its experimental verification in the recommendation system. So what is the motivation behind it? So overfitting is a common problem. So how we can get rid of overfitting, but at some extent. So the randomly dropping of the neurons to dropping of the neural structure and dropout has achieved the great success in improving the model performances. Despite of their wide application, one dropout method which works for the one model structure, it may or may not work for the other model structure. So there is a need, there is a need of compressive survey based on which dropout method is suitable for which model structures. So this survey is all about that. So coming to introduction, dropout is operation is not only dropout of the model structure but also dropout of input information. So here in this survey paper, they have classified the dropout methods and summarized their effectiveness in application scenarios. There is a comprehensive review of more than 70 dropout methods along with their granularity, and experimentally they have investigated effect of dropout methods in the recommendation scenario. So problem statement is there is a need of the systematically review the previous dropout methods and classify them into the proper some categories. So there is a need to design taxonomy is which easy to understand and capable of including new dropout methods. And the most of the methods with the commonality also fail to compare their results under same scenario, since the dropout methods are applied to different forms of input informations and model structures. So there is a need of the common proper comparison scenario which should have rich heterogeneous input information, which apply to various different model structures. So this is the taxonomy of the dropout methods. The three main categories are dropping of the model structures, dropping of the embeddings, and dropping of the input information. In this presentation, I have specifically focused on dropping of the individual neuron, how it's done, and these are some dropout methods which I come across while this survey. Like Hinton has proposed the idea of dropping of the neurons, which prevents the complex coadaptation on the neurons during the training of the data. During the training to the model. Then we have drop connect, which is randomly drop neuron connection instead of neurons. For the CNN, we have spatial dropout, which randomly drops the feature map. Then drop block, which drops the continuous region of neurons to prevent overfitting. For RNN, there is early applications of dropout, which not only only drop the feed forward connections in order to preserve the memory ability of RNN. There is other methods for RNN like RNN drop and recurrent drop, allow a dropping of the recurrent connections as well. So let's deep dive into dropping of individual neurons, what it actually means, like how it's done. So as we came across various neural network like this, there is an input of y of 0, and these are the weight and biases, and this then we are getting output of this to end, which is provided input to the next layer like this, and this output is again weights and biases multiplied, adding with some biases and given as a output. This is a simple neural network with the one layer. So without dropping off any neuron, we formally follows this equation like output of the current layer, lth layer will be the multiplication of input and yi and plus biases, and then this output has gone through the function and which is given as input, which is the input to the next layer, that is y of il plus 1. So how this, how we drop off the, what is the meaning of dropping off neuron? So here dropout set proportion of a p, like proportion p is a follows some probability distribution here. We can see the r of suffix j is follows the Bernoulli distribution of probability p, and here and here each of the probability P is multiplied with the y of L, like output of this current layer. We will decide the which output we need to make 0, uh, uh, like dropout ratio of the neuron outputs to 0 during the training. So here we get modified output y of suffix L, which is there is a some sign, there is a sign on top of it. So this symbol is represent the modified output of the neuron based on this probability distribution, like which neuron we want to drop out. So modified output of the current layer we get as W of I L, suffix x L plus 1 y of L plus V of I, which will get further improvised output as y of I L plus 1, and which is function of z of I L plus 1. So that's how dropout is performed based on the probability. So, but here is a point to be noted that during the testing we don't perform dropout, like whatever weight we have already modified with the probability P distribution. Over here we have multiplied with the uh, output of the each layer with the probability distribution of R. We have to again, if we have multiplied the weight with the probability, then we have to again make them consistent by dividing by multiplying with the probability. But here I have shown that like output of the current layer I have multiplied with the probability of R, if we are if we are making modifications to output of the current layer. So that's how the dropping of individual neurons is performed. So dropout in action, like without any of this dropout method, here we can see in the graph, like here the feed forward neural network originally consisting of 160 errors on the test set, but once we perform the 50% dropout on the neurons, we get a error get reduced up to 130. And further, if we perform the dropout on some input information, errors get reduced up to 110. Then these are the some use cases like they have performed the experiments on these 4 models, like recommendation models, like traditional recommendation model, neural recommendation model for utilizing context information, sequential recommendation model, and the graph recommendation model like GCM. So these are the 4 models, and these are the 4 dropout methods. Each of the like dropping model structure, dropping input information, dropping of embeddings, and dropping of graph information. These dropout methods has been performed on these models. This is the dataset statistics which are used for the carried out our experiment on the dropouts. So dropout experiments in the recommendation models are, like here we can see in this graph. On the x-axis we can see all the models which we have discussed in this slide, and then on the y-axis we have NDCG at 10, which is evaluation metric based on each of the dropout, how much model performance is, how much performance model is giving. So as we can see, originally the structure without dropping of any structure, like we are getting the accuracy evaluation metric is very low, but as we do various dropout on model structure, dropout on information, we get significantly very good performance on the significantly very good performance on the these models. So coming to the conclusion, the experiments has been performed on 5 recommendation model to perform effectiveness of the each dropout methods, and at the end here we found that the dropping of the model structure is has most general and stable improvement, instead of dropping of the input information and dropping of embeddings. These are the model specific, like Dropping of input information and embeddings may work for one model, may not work for another model, so they are model specific. So